Hello everyone. In this video, I'm going to show you how to design a low-pass filter in RF microwave frequency on a PCB. So you may be designing the filter in microstrip or coplanar waveguide. So I'm going to show you how to do it. Now, first of all, in a filter, you may end up with something with inductor, and you might also end up with something like capacitor. And you have two options. You can either realize this filter by replacing the the inductor, with the lump elements. So lump element is one approach. But there's the problem about the lump element filter design. First, uh, there is the issue about the availability of components. For example, the capacitor, you may not be lucky enough to get a capacitor with certain value. For example, 0.3 uh, nano farads, right? This kind of capacitor is hard to find in the market. And in a planar circuit, you might be able to do it flexibly according to the area, the geometry. But then, right, you also face a problem about the inductor. Inductor is not easy to implement in RF microwaves frequency. In RFIC. So what you can do now is to use uh, other methodology. Uh, say, for example, microstrip. Coplanar waveguide. Uh, so you can use this, and in this case you don't need to worry about certain values of uh, inductor or capacitor, and all the value will be realizable by changing the geometry. So now let's take a look in one example. Suppose you need to implement an inductor. The way how we can do it is to use a transmission line with a short circuit. We can use a short circuit stop. So this is the transmission line, and it's a short circuit. So this is the yeah. Let's make it like this. So this is the transmission line and short circuit, and the length here is equivalent to 45 electrical degree. And let me explain to you why we can do that. So in an inductor, you have a uh, inductive reactance represented by J omega L, and for a transmission line, you can work out the input impedance by using the formula here. J, and then Z log tangent beta L, and then like this. So tangent 45 degree is equals to 1. And uh, uh, when the low is short circuit and the output is short circuit, this means ZL is equals to 0. So in this case, if we substitute Z is equal to uh, Z of L equals to 0, and uh, we replace beta L with 45 degree. Then what we can get here is 0 plus V log, and then uh, tangent 45 degree is 1, and then V log, and then the other term is 0. So altogether, we will get this one. So in other words, uh, in order for the input impedance to be equal to uh, this inductive value, we can just make sure um, we can use this. So as a result, the actual inductance is going to be equal to V naught divided by omega. So this is one approach. Uh, so the inductor might have two end, A and B, and A will be used here, B will be used here. So you can use this way the increment and inductor. And on the other hand, for a capacitor, and we also have J, B, and Z, and the uh, reactant is going to be J omega C. So in this case, you can use an open circuit stop to realize this capacitance. So if we do this, then we will have open circuit stop here, and I will use A here and B here, and the input impedance here is going to be Z of in, and the length here is also 45 degree. So in this case, if we use the transmission line formula here to calculate the input impedance, I will need to substitute ZL equals to infinity. So ZL will be infinity, and uh, for exactly the same reason, here will become tangent will become 1. Tangent 45 degree will become 1. So here we have Z naught and infinity. So something like this, right? By the way, we cannot do this. We have to do it carefully, yeah? J and then infinity and then tangent beta M. So if we divide the top and bottom by infinity, so what we will get here will be a little bit bright. A little bit bright. So what we have here is uh, the top one So this one will be 0, uh, and this one here will be equals to uh, minus j cotangent uh, minus j is 0, minus j is 0, is it right? Cotangent minus 1, yeah, okay, 0, yeah, I think so. So as a result, you need to be able to equate this to j omega c. So from here, I can say uh, the capacitance that I need uh, will be omega v naught, and this is the capacitance, and this is the inductance. Uh, Either way, if you want to find the inductor, then you will get omega L. Z naught is equal to omega L. If you want to find the impedance equivalent to the capacitance, then you will need V is equal to omega. So sorry, V naught equal to omega C. So you use the characteristic impedance of the transmission line of the open circuit stop or the short circuit stop uh, to to match with the capacitance and inductance. This way of replacing the inductor and capacitor with their respective open circuit stop or short circuit stop is so-called retrace transformation. Retrace transform. Okay, so this is the first episode. So let me show you an example. Let's have a look in an example. Uh, Suppose you're going to design a low pass filter with cutoff frequency um, 4 gigahertz, and the characteristic impedance is going to be equal to 50. This is the reference impedance. So here we go. So uh, depending on the requirement on the roll off, suppose the design is just right here. The value has been given. Say this one is 3.3. So this is uh, temperature or butterworth. And the capacitance here is 0 cent. And here is 3.348. So what we are going to do next is to replace those inductance and capacitance here with open circuit stop and short circuit stops. So like what I have said to you, the inductance omega will be equals to um, now first of all, right, we need to work out the V value first. So this is the normalized circuit. And we need to find the V1. So what we can do here is uh, to find out the nominal value. And here you will need L equals to the normalized value times the characteristic impedance divided by the omega. Omega naught, the cutoff frequency. Sorry, cutoff. So 3.348 times 50 divided by 2 pi and then 4 giga. So this is what you need. So by my calculation here, I got 0.66 vision. So similarly, the before doing this, I will write down here. So 66 nano. And similarly, the capacitance will be equals to Cn and then omega. So 0.7117 divided by 50 and then 2 pi 4 times 10 to the 9. So if you work out very carefully, you will get 0.66 pico. So this is the real one. So it's not a normalized one. Okay. So this is ultimately the lump element version of the filter that the question asked for. But of course, in this chapter, we are going to learn to use the planar circuit to realize this inductance. So we are sure you won't be able to find this kind of inductance, 0.66 nano, right? It is so small. It's unlikely possible for you to buy this kind of inductor. This kind of inductor is non-existent in the market. So what we can do here is we can temporarily, let me erase the, so you can use open circuit stop as you can use short circuit stop to implement this one. And we can use open circuit stop to implement the capacitor. So in this case, V dot, for example, this is 1 and this is for the inductor, will be equal to omega not cutoff and then error 1, so 4 giga times 0.66 length. And you work out carefully, you've got 167 point. So this is the required inductor impedance. This will be the required impedance of the open circuit stop. Open circuit stop. So likewise, you can say here is the cell, because it is symmetric. And now this one will be based on a short circuit. Sorry, this one will be based on short circuit stop. Short circuit stop. And this one will be based on open circuit stop. So open circuit stop will be 1 over C and then C dot C2. And then 4 giga and then 0.566 peak. And as a result, if you work out very carefully, you will find this impedance. So in other words, your transmission line will become your printed circuit board will become like this. So you have one open circuit stop. So I'm going to put in the middle. Yeah. And this one is 70.3 ohm. And you have another one. And this will be based on a series open circuit stop. So short circuit stop. And the length here will be lambda divided by A. And similarly, this one is also equal to lambda G divided by A. But different from the middle short circuit stop. The stop for realizing the inductor has to be short circuit. So this is one. So the impedance for this one will be 167.4. So this is the pin circuit version of your low pass filter, and you will work. But there is a problem as well. In RF microwave, it's easy to implement a open circuit stop, but it is not easy to implement a short circuit stop, and that's why we need another methodology. There is a way to convert the short circuit stop into open circuit stop, and this is going to be discussed in the next video. Right now, if you have any question, please leave your question to the comment section of the video. Thank you.